Hello students, in this video we are going to see other difference operators. In which first operator is shift operator. The shift operator. The operator E is called shift operator. The operator E is called shift operator or displacement or translation operator It shows that the operation of increasing the argument value of x by its interval of differentiation h. Therefore, E of f of x is equals to f of x plus h or E y x is equals to y x plus h. Okay, see here the operator E is called shift operator or displacement or translation operator. It shows that operation of increasing the argument value of x by its interval of differencing h means E of f of x is equals to increase the value of x by h means E of f of x is equals to f of x plus h, or this can be written as E of f of x can be written as E y x is equals to y x plus h. Okay. Therefore, E square of f of x is equals to E of f of x, okay, which is equals to E of f of x is f of x plus h. E of f of x plus h. Okay. Value of x is increasing by h. Okay. Now we have to calculate E of f of x plus h means here x plus h argument x plus h is increasing by again h. It becomes x plus 2h. Therefore, which is equals to f of x plus 2h. Okay. Similarly, E cube of f of x, E cube of f of x is equals to f of x plus 3h. Here E square f of x is f of x plus 2h. Therefore, E cube f of x is equals to f of x plus 3h and so on up to E raised to n of f of x is equals to f of x plus nh or e raised to yn yx is equals to yx plus nh. Okay. Now e inverse is equals to f of x minus h. For e of f of x, we add h in x, and for inverse we subtract h from x. E raised to minus 2 is equals to f of x minus 2h, and so on up to e raised to minus n is equals to f of x minus nh. Okay. E raised to 1 by 2 is equals to f of x plus h by 2. Okay. The operator E inverse is called inverse operator of the operator E. Okay. E of f of x is f of x plus h, and E inverse of f of x is f of x minus h. Okay. Next operator is differential operator. Second operator is differential operator D. Differential operator D. Okay. The differential operator for a function y is equals to f of x is defined by d of f of x is equals to d is here d by dx of f of x. Okay. D square of f of x is equals to d square upon dx square f of x, and so on. Differential operator is denoted by d, and d is d by dx. Therefore, d of f of x is equals to d by dx of f of x, and d square f of x is equals to d cube dx square f of x. D cube f of x is equal to d cube upon dx cube f of x, and so on. This is the differential operator D. Next operator is unit operator 1. See the unit operator 1. Okay. The unit operator 1 has the property that 1 into f of x is equals to f of x. It is also called identity operator. Identity operator. It is also called identity operator. Okay. Next operator is averaging operator. Mu. the operator mu is a averaging operator and is defined by mu of yx is equals to 1/2 of yx plus h by 2 plus yx minus h by 2, or mu of yx is f of x, which is equals to 1/2 yx plus h by 2 is f of x plus h by 2 plus f of x minus h by 2. The operator mu, it is a averaging operator and it is defined as mu of yx is equal to 1/2 of yx plus h by 2 plus yx minus h by 2, which there, or mu of yx is nothing but f of x, which is equals to 1/2 f of x plus h by 2 plus f of x minus h by 2. Let us see properties of operators. Properties of operators. Properties of operators. Okay. First property is the operators delta, del, e, delta, mu and d possesses the linearity property. First property is linear property. For example, consider delta of C1 f of x plus C2 g of x. Use definition of delta, which is equals to C1 of f of x plus h plus C2 g of x plus h minus in bracket C1 f of x plus C2 g of x, bracket complete. Okay. Which is equals to, observe this here, in this term and in this term C1 is common, so take it outside. C1 into f of x plus h minus f of x, okay, plus C2 into g of x plus h minus g of x, okay, which is equals to C1 into delta f of x plus C2 into delta g of x. Delta of C1 f of x plus C2 g of x can be written as C1 into delta of f of x plus C2 into delta of g of x. Therefore, delta has linearity property. Similarly, we can show that other operators del, e, delta, mu and d also have linearity property. Okay. On substituting substituting C1 is equals to 1 and C2 is equals to 1, in this equation we get delta of f of x plus g of x is equals to delta of f of x plus delta of g of x. Okay. Also substituting C2 is equals to 0, we get delta of C1 f of x is equals to C1 into delta of f of x. Second property is the operator is distributive over addition. The operator is distributive over addition. For example, delta of f of x plus g of x can be written as delta of f of x plus delta of g of x. Therefore, delta operator is distributive over addition. Okay. Third property is all operators follows the laws of indices. For example, delta a raised to b, delta raised to b of f of x is equals to delta raised to a plus b of f of x, or which is equals to delta raised to b, delta raised to a of f of x. Delta raised to a, delta raised to b of f of x is equals to delta raised to a plus b of f of x, which is equals to delta raised to b, delta raised to a of f of x. Okay. Fourth property is E and delta are not commutative with respect to variables. That is, delta of f of x into g of x is not equals to f of x into delta g of x. Okay. And last property is, if delta of f of x is equals to 0, then it does not mean that either del is equals to 0 or f of x is equals to 0, because this del is a operator on f. It is not a product. Therefore, here delta is, this is not a product, and here delta is operator on f. Therefore, del of f of x is equals to 0 does not mean that either delta is equals to 0 or f of x is equals to 0. Let us take relation between different operators. Relation between different operators. first relation is delta is equivalent to E minus 1 or E is equivalent to 1 plus delta. Second is E del is equals to del E, which is equivalent to delta. Third relation is del is equivalent to 1 minus E inverse or E is equals to 1 minus del inverse. Okay. Fourth relation is E is equals to E raised to h d is equivalent to 1 plus delta, where d is a differential operator. D is differential operator. D is differential operator. Fifth relation is delta is equivalent to e raised to 1 by 2 minus e raised to minus 1 by 2. Sixth relation is mu is equivalent to 1 by 2 into e raised to 1 by 2 plus e raised to minus 1 by 2. And last relation is del of e raised to 1 by 2 is equivalent to delta of e raised to 1 by 2 is equivalent to delta. Let us see proof of this relation. Proof. In first relation, we have to prove that delta is equal to e minus 1. Okay. We have e of f of x is equals to what? F of x plus h. Okay. Delta of f of x is equal to f of x plus h minus f of x. Okay. Which is equal to, here e of f of x is equals to f of x plus h. So f of x plus h is equals to e of f of x minus f of x. Take f of x common, f of x into in bracket e minus 1. See here. Okay, e minus 1 into f of x. Okay. Here observe that delta f of x is equals to e minus 1 f of x. Therefore we get delta is equals to e minus 1. Okay. From this, e of f of x is equals to what? Delta of f of x plus f of x. From this equation, delta f of x is equals to e of f of x minus f of x. Therefore e of f of x is equals to delta f of x plus f of x, which is equals to delta plus 1 into f of x. Okay. Therefore we get e is equals to delta plus 1. And from this equation, delta of f of x is equals to e minus 1 into f of x, we get delta is equals to e minus 1. Therefore we have hence delta is equals to E minus 1 and E is equals to delta plus 1. Hence, first relation is proved. Okay. Here remember that this one is a unit operator. We have seen that unit operator is denoted by 1 and it is nothing but 1 of f of x is equals to f of x. Let us prove relation number 2. In 2, we have to prove that E del is equal to E del is equal to del E, which is equivalent to delta. Okay. E of del is equal to, okay, here we operate E of del on f of x, we get E of del of f of x, okay, which is equals to E of del of f of x is f of x minus f of x minus h. Okay. Operate E on f of x and f of x minus h. We get E of f of x minus E of f of x minus h. Okay. E of f of x is f of x plus h minus E of f of x minus h. This x minus h is increased by h, means x minus h plus h, which is equals to x. Therefore, E of f of x minus h is nothing but f of x. And we know that this is the definition of delta of f of x. Okay. Therefore, we get E of del is equals to delta. Call this equation number 1. Okay. Now we have to prove that del E is equivalent to delta. Okay. Del of E is equals to del of E of f of x. Okay. Del of E of f of x is f of x plus h. Okay. Which is equals to del of f of x plus h is f of x plus h minus f of x, which is nothing but delta. Call this equation number 2. From 1 and 2, we get E of del is equals to del of E is equals to delta. Hence, relation number 2 is proved. Okay. Now we will prove relation number 3. In 3, we have to prove that del is equivalent to 1 minus E inverse, or E is equals to 1 minus del inverse. Okay. We have del of f of x is equals to f of x minus f of x minus h. Okay. Which is equals to f of x minus, this is the E inverse of f of x. We have already discussed that E inverse of f of x is equals to f of x minus h. Okay. Here in these two terms f of x is common, therefore take it outside. In bracket remains 1 minus E inverse of f of x. Okay, therefore we get del is equals to 1 minus E inverse. Okay, therefore minus E inverse is equals to del minus 1. That implies E inverse is equals to 1 minus delta. Okay, multiply on both sides by minus 1. Get E inverse is equals to 1 minus delta, and therefore this E inverse is nothing but 1 upon E. Therefore, taking reciprocals on both sides, we get E is equivalent to 1 minus 1 minus del inverse. Okay, hence relation 3 is proved. Now we will prove relation number 4. Here we have in part 4, in relation 4, we have to prove that E is equivalent to E raised to HD. Okay, we operate E on f of x, we get f of x plus h, which is equal to f of x plus h into f dash of x plus h square upon 2 factorial f double dash of x plus and so on. This is by using Taylor's theorem. F of x plus h is written as f of x plus h into f dash of x plus h square upon 2 factorial f double dash of x plus and so on. Okay, here this is 1 into f of x plus h into, here f dash of x is nothing but dy dx of f of x, and we know that dy dx is capital D. So here we write d of f of x plus h square upon 2 factorial as it is. This is f double dash, double derivative. Therefore d square of f of x plus and so on, which is nothing but e raised to hd f of x. See, it is here since e raised to x is equals to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus and so on. If you e raised to x is equals to, suppose if you put x is equals to hd in this series, then you get e raised to hd into f of x. Okay, therefore e of f of x is equals to e raised to hd into f of x. Very simple. E of f of x is equals to, we know that f of x plus h. By using Taylor's theorem, this f of x plus h can be written as like this, and here f of x can be written as 1 into f of x plus h into f dash, means first derivative of f with respect to x. Therefore here dy dx is replaced by capital D and plus and so on. Okay, which is equals to, this is e raised to hd f of x, since by e raised to x is equals to this. Therefore e of f of x is equals to e raised to hd into f of x. Therefore E is equals to e raised to hd. Okay. Since in relation 1 we have proved that e is equivalent to 1 plus delta. Therefore, delta is equal to e minus 1, which is nothing but e raised to hd minus 1. E raised to hd minus 1. Here is equivalent. Therefore, e raised to hd is equivalent to delta plus 1. Okay. Hence, we have proved relation number 4. Now, we will prove relation number 5. In relation number 5, we have to prove that e raised to 1 by 2 minus e raised to minus 1 by 2. Okay. Delta of f of x is equal to f of x plus h by 2 minus f of x minus h by 2. Okay. This f of x plus h by 2 is e raised to 1 by 2 minus e raised to minus 1 by 2. Here is of f of x minus f of e raised to minus 1 by 2 of f of x. Okay, which is equal to, this can be written as e raised to minus 2 minus e raised to minus 1 by 2 of f of x, which is equal to delta is equivalent to e raised to 1 by 2 minus e raised to minus 1 by 2. Hence, fifth number relation is proved. Now we will prove relation number 6. In 6, we have to prove that mu is equivalent to 1 by 2 into e raised to 1 by 2 plus e raised to minus 1 by 2. Okay. For this, we take mu of f of x, which is equal to, we have discussed definition of mu, 1 by 2 of f of x plus h by 2 plus f of x minus h by 2. Okay, which is equal to 1 half f of x plus h by 2. Here it is e raised to 1 by 2 of x. Okay, plus e raised to minus 1 by 2 of, here is f of x plus e raised to minus 1 by 2 f of x. Okay, which is equal to 1 by 2. Here f of x is common, so in bracket remains 1 half into e raised to 1 by 2 plus e raised to minus 1 by 2 into f of x. Therefore, we get mu is equivalent to 1 by 2 into e raised to 1 by 2 plus e raised to minus 1 by 2. Okay, hence we have proved relation number 6. Now we will prove relation number 7. In 7, we have to prove that delta of e raised to 1 by 2 is equivalent to delta. Okay. Delta of e raised to 1 by 2 is equivalent to delta. Okay. Delta of e raised to 1 by 2 of f of x. Okay. This can be written as delta of e raised to 1 by 2 of f of x. Okay, which is equal to delta of e raised to 1 by 2 of f of x is f of x plus h by 2. Okay, and delta of f of x plus h by 2. Okay, let us see here. Delta f of x is f of x plus h by 2 minus f of x minus h by 2. Okay. So here x is replaced by x plus h by 2. Therefore delta of f of x plus h by 2 is f of x plus h by 2 plus h by 2. X plus h by 2 plus h by 2. H by 2 plus h by 2 is 2h upon 2, which is x plus h. F of x plus h minus f of x minus h by 2 means x plus h by 2 minus h by 2. H by 2 h by 2 cancel. Here remains only f of x. Okay, which is equal to, this is the definition of delta, which is equal to delta of f of x. So delta e raised to 1 by 2 is equivalent to delta. Hence we have proved all the relations between different operators. Okay.